Today, I'm going to talk about the lean proof of systems. It's not going to be a technical talk. I just want to make an introduction and talk about the challenges. What's lean? Right? Lean is a proof of systems and also programming language. It's based on dependence type theory. The main goals of the project is to provide a proof of systems that is extensible, is very expressive, it scales really well in its performance. We view it as a platform for formalized mathematics, software development and verification, and also a platform for developing custom automation in domain-specific languages. We have a small trusted kernel, and you can even check your proofs with external checkers if you want. You can view Lean as a development environment for formal mathematics. All proofs and definitions are machine checkable. The math community using Lean is growing rapidly. I feel like they love the system. Yeah. You can view Lean also as
a we do.
Yeah. We can view it as a compiler for mathematics, right? You have this high-level language. Nobody wants to use the kernel codes, right? I talked about this small trusted kernel. This is like assembly language, right? You can view Lean as a compiler also that goes from high-level language or what Andre yesterday mentioned, vernacular, to this kernel code, right? Here I have a small example on VS Code. VS Code, I think, is the favorite IDE that the community uses. It's not my favorite editor. I'm ancient. I use Emacs. But this VS Code, how it looks like. Just like codes. You can learn more about Lean in this website, leanprover.github.io. I want to invite everybody to install Lean. It's very simple. If you have VS Code installed in your machine, you just have to download the Lean 4 extension, right? Everything is going to be installed automatically for you. It's super convenient. And I think it's very addictive. I mean, people tell me that's an addictive system. We like to believe that to enable decentralized collaboration. And there are two main ingredients in this story. We have a metaprogramming. What's metaprogramming? It's the ability to use Lean to extend Lean itself. You can you can create your own proof automation using Lean. You can create visualization tools. You can create your own notation. For example, this visualization that was created automatically. This visualization on the bottom of the slide was created automatically by a tool that Patrick Massot wrote, right? Creating this kind of automatic visualization is important. And also, it's not an accident that we want users to extend Lean using itself. We have very little resources, and one way to it's impossible for us to append everything the community wants, and allowing the community to extend the system by themselves is really important, right? Another ingredient is formal proofs, right? Formal proofs are important because you don't need to trust me to use my proofs. You don't need to trust my proof automation to use it. Especially the proof automation, it's really powerful idea, right? You can hack a new proof automation without fear of introducing unsoundness to your system, to the system, right? You know that at the end, the kernel will check your proof. I think this is a very powerful idea. Here I have a very simple example in Lean 4. The Mathlib is more than 1 million lines of code. They are moving now to Lean 4. More than 30% of Mathlib has already been ported to Lean 4. And I'm going to show a few examples. Here you have this notion of a class. You have like a class called strib that says a type alpha has this property you can view as has the property of having this strib property if it implements multiplication and addition. And multiplication and addition have satisfies these two extra properties. They have left and right distributivity. And now you can say a ring, a type alpha is a ring If it has is an additive commutative group, is a monoid, and has this strip property. Then you can define matrices, you can declare your own notation, right? For example, here we're defining the syntax, adding new syntax to the system, saying how, giving the semantics with these macro rules, how you expand the syntax in existing notation. Macros are important because we want in Lean, simple extensions should be simple to implement. Here you just want the square brackets notation for matrices, right? So you want to be able to write X square brackets, I comma J, close square brackets. You want it to make it very simple. Here, 2 lines of code, you can do it, right? So simple things should be simple. That's the idea we want to communicate with this example. And you can say a matrix, a square matrix that is where n is a finite type, n has decidable equality, alpha is a ring. This is the square matrix is also a ring in this case. You have theorems in Lean. You express the theorems with the notation you define it. There's a lot of meta information in our theorems. Like in this example, you see the at square bracket simp. This is a meta information telling the system that this theorem, that is an equality, should be used as a simplification rule by the system. So you have all this kind of meta information in Lean. A recurrent question we get is, should we trust Lean, right? Then we say, yeah, you should trust. Lean is a big system, has many bugs as any big system. But you only have to trust the small kernel, right? The small kernel is around 10,000 lines of code. You may ask, well, 10,000 is a lot. Should I trust the kernel, right? This is small checker. Yeah, if you're concerned about that, you can export your proof and check it with external checkers implemented by the community in many different languages. If that's not enough, you can implement your own checker. You have access to all data structures. Lean is implemented in Lean, and you have using Lean, you don't need to learn a new programming language. The same language you use for writing math, we use it to implement Lean itself. And you can introspect on the state of the system. And by introspecting it, you can export to any form. You can create your own export formats and check your proofs using your own checker. Mathlib, it's beyond any expectations. When we started the project like 9 years ago, we would never expect that one day Mathlib, you would have a mathematical library with more than 1 million lines of code, right? The community is huge. Here, putting the maintainers for Mathlib. Sorry that it's not up to date, the list of maintainers, but I was blown away by the community. Just to put in perspective, there's a paper, the Lean Mathematical Library is authored by the Mathlib community because it would be impossible to list everybody that contributed to the library. The statistics are also very impressive. I mean, Mathlib starts in 2017. You see the growth. It's more than 1 million lines and keeps growing. And after the transition to Lean 4, we expect it to grow even faster. And Mathlib is a foundation to many other projects like the Lean Perfectoid Spaces. Some people talked about these projects already, but I thought it was a really nice twist, right? Before this project, many people viewed proof assistance as a tool for ensuring your development is correct, your theorem is correct, the proof is correct. And this project shows that it's not just about correctness, it's also about communicating ideas. Here, if someone wants to understand what a perfectoid space is, they can browse the definition, they can jump. For example, if you don't know what a Tate ring is, you can jump to the definition, you can zoom in, zoom out, you can create visualizations automatically, you can treat math as data, and you can process this data. I will talk also a little bit about the ecosystem, right? You have the Lean developers, but you have mathematicians, a big chunk of the community. You have Mathlib, who had in the past projects like formal abstracts, flight pitch, perfectoid spaces, the liquid tensor experiments. People talked yesterday. This is great. We are super grateful for all these impacts by the math community. Another part of the ecosystem is AI research. Both OpenAI and Facebook AI have developed AI assistants for Lean. There is the IMO Grand Challenge. That the goal is to create a system that will get a gold medal in the IMO. Right? For example, OpenAI was trying to achieve this goal by building a math assistant on top of Lean. We think this kind of effort is really interesting, and we want to support that with Lean. We also have software developers. Okay, we have software developers, right? The message here that's a great language for math is also a great programming language. As I said, we implement Lean using Lean itself. One of my managers like to say that Lean is a language where you program your proofs and you prove your programs. And we have applications like people use Lean to control robots. There are people that use Lean for verifying smart contracts, and we want to support this kind of application. And there are also students, right? We think self-motivated students with no formal access to math education can learn math, right? There are many smart kids without formal math education, access to formal math education, and they can learn math by themselves using a system like that. The same way we can find kids without formal access to computer science education, they learn to program, they become amazing computer scientists following tutorials, using a playground. For computer science, a playground is a programming language, a compiler, an interpreter. Lean can be viewed as the same kind of tool for mathematics. I also invite everybody to go to the Zulip channel. It's really amazing. You find people like Peter Scholler there. You have AI researchers. You have people commemorating results, students asking for feedback, people talking about what they did with Lean. It's really inspiring place to. The mathematical library, as I said, was beyond all my dreams. The impact it had. You can find articles on Wired, Quanta. We are super grateful for everything the math community did. The liquid tensor experiment was also very instrumental. I will not talk a lot about this project since yesterday we had a talk about it. But here, I think the main message is projects like that help us addressing the main challenge this kind of project has, funding. I will talk more later. One topic I want to talk about is the impacts on formal mathematics. I think there's this talk, but Johan Kommelin on the Fields Institute, I invite everybody to watch. It's really great talk. And one message I got from his talk is like, in the future, there will be mathematicians that will operate like engineers, right? When Johan explains the project, explain the liquid tensor experiment in this talk, and talk about creating abstraction boundaries in mathematics, where you create well-defined interfaces where people can work in modules independently of each other. These are the same kind of techniques people use to develop software at scale, right? And this is great. We will have in the future mathematicians that are like great engineers. And I can tell by Johan's talk, he would be a great engineer if he was a computer scientist. But some mathematicians may feel like, wow, I don't want to be an engineer. This is horrible. Well, there's no reason to fear that. There are many computer scientists that they are not great engineers. There are great computer scientists that never write a single line of code. They create the vision, they create new concepts. The same thing will continue in math. There will be people that are only, at least, of course, I'm not a mathematician, I cannot say, but I can only make the parallel with computer science. And in computer science, you have people that work on big ideas, visions, new techniques at the very abstract level. You have people that are great engineers and people that are great coders, right? People that will, it's like after Johan set up all these interfaces and add them to, there are a lot of people filling these modules they define as, right? These are like great coders. Same thing, computer science. So there's space for everybody, right? And I invited everybody to watch this talk. It's really great. Extensibility, right? I want to emphasize this in the project. Mathlib is not just math. It has many Lean extensions, right? If you check Mathlib, it's more than 1 million lines of code, but it has 50,000 lines of Lean extensions there. The community is extending Lean using Lean itself. In Lean 4, we want to make sure that every single part of the system is extensible. Here I have a small tactic. It's a small extension. It's a piece of proof automation, the ring tactic. It's much bigger. This is just the final piece of code that's for this extension and was written by the community. They didn't have to talk with us. They did completely independently of us. And I think this is great. That's what we want to see, right? That's a way to make sure that everybody can extend the project in the direction they want. These extensions, because people are writing these extensions, it's really important that Lean is also efficient programming language. We want these extensions to be performance, right? And Lean is an efficient system. Lean 4 is an efficient system. Just to highlight some ideas, for example, the Lean Memory Manager, right? This is a colleague of mine, Dan Lyon. We were talking with him about the Lean Memory Manager. We want to allocate memory more efficiently. It sounds like a trivial problem, but it's still a very challenging problem today, right? There are many different techniques for allocating more memory efficiently. And we worked together. He designed a new memory manager for Lean, a new algorithm. It turns out this algorithm that is used in Lean now is now also in the Bing memory manager, right? It's the same memory manager now used by Bing search, right? He managed to reduce latency. He saved millions of dollars. And this kind of success story is also important to keep the projects funded, right? So, it's like sometimes people feel like, I see Kevin, I saw Kevin in the audience. He mentions like, oh, Microsoft, there's no Microsoft in the projects, right? Our CEO doesn't even know Lean exists, right? These are research projects, and to keep it funded, success stories like this one are important. Success stories like from Mathlib are important, right? Another feature is this function in but in place technique, right? That's in Lean. Lean is a pure language, pure functional language, but it performs destructive updates when it's safe. The compiler knows how to do that for users. And this was key for us to achieve high performance. As I said, we want simple extensions to be simple. We want users to be able to define their own extensions, their own notation. And in Lean, we have a hygienic macro system. What does that mean? What does that mean to be hygienic? Hygienic macro system is a macro system that you cannot perform accidental name capture, right? And the Lean macro system has this property. You can define syntax and you can define macros, how to transform the syntax that you just added in existing notation. Term is one of the syntax categories we have in Lean, but you can create your own. We have many different syntax categories. Even the syntax for defining syntax is defined as using its own syntax category. And you can define your own categories if you want. Here you have an example to illustrate what hygiene is in action. Suppose that you want to define a new notation, const E. Const E means you want to define a constant function that returns always E, an expression, a term, right? And you're telling that const E should be expanded in fun X arrow E, basically saying that given an X, you're always going to return E. But suppose that E contains the variable X there. You don't want it to be accidentally captured by this X here, because otherwise it would not be a constant function. And we make sure that this will not happen. Same thing if I create an auxiliary function, like here in the second example, I have def my elaborator. I'm creating a name, and I want to make sure that this my elaborator, this name I'm creating, the macro is creating, is not accidentally captured, right? It's going to be a fresh name every time the macro is executed. This makes sure that simple things are simple to implement. And this capability help us to implement Lean itself. We create many domain-specific languages inside of Lean to implement Lean itself. For example, here we have a do notation is a domain-specific language that allows us, in a pure language like Lean, to write code that looks like imperative. In this example, if like you have E that's a polynomial, and you have A an assignment, and you want to return an optional rational number as the results. And you want to, we're going to start by saying that you have a R that's a mutable variable, and we're going to have a for loop traversing the polynomial. The polynomial is a pair of coefficient and variable. We are going to try to use the assignment to check what's the value of the variable. If the variable is not in the assignment, we are going to fail return none. Otherwise, we're going to keep incrementing R, updating the result R, right? And it's going to return R. The code looks imperative, but this is just notation. The macro system, this domain-specific language, converts that in pure code. Behind the scenes, this is all pure, right? It's just notation to make things convenient for the user. And we use this notation to implement Lean, right? Here we have, it's not important to explain this example, it's just to say this is part of the Lean implementation. That's the message. This is building a congruence proof. We have a simplifier in Lean. We create congruence proofs where when you have f of x equals f of y, if x equals y, you want to create a proof that f of x equals f of y. This code here works if you have an arbitrary number of arguments, and was written in Lean using this notation, this do notation. Another GSL we have is the TATIC framework, or you can also view it as a synthesis framework. What's the idea here? Mathematicians, they love this static framework, where you're basically constructing the proof interactively with the system. You can say, oh, I want to use induction. I want to apply this theorem that I proved before. I want to introduce this variable. I want to do proof by cases, right? You have these many different tactics you use to construct your proof interactively. And you can view this language as a domain-specific language that was built using this framework I just described it. And all the built-in tactics we have been implemented in Lean, right? And here's just the case analysis one, and the users can add their own tactics, and they do it. Mathlib has many of these extensions. And I think this is important. It's impossible for us to implement every single feature the community wants. Challenges. This was just an overview, but I want to focus on the challenges now. There are many different dimensions. One of them is automation, right? If you open any math textbook, you're going to find proofs when people say this is obvious. Yes, that many steps are obvious. You don't want to waste time. And in a proof of system, this is obvious is filled by proof automation, right? We have a lot of proof automation in Lean, but the overhead factor is still really high. The overhead factor is when you compare informal math developments with the formal version. If, for example, for the liquid tensor experiments, people estimated the overhead should be 20, right? It's really high, right? By reducing the overhead, you make the technology more attractive to a bigger audience, right? We have a lot of experience on automated to improving, but dependent type theory is very challenging, right? It's way harder than first order logic to automate. And one challenge in these domains, can you reduce the overhead factor to 1 in a distant future? Can it be less than 1, right? If it's less than 1, would be awesome, right? It feels like now you can use a proof of system on a daily basis to make you faster, right? To write down a paper, for example. Scalability, right? This is another big challenge, right? Formal mathematical objects are massive, right? In Mathlib, if you try to print these objects in full detail at the kernel level, right, they're insanely big, several pages, right? And this is a recurrent problem. We are currently fighting for the scalability issues, right? It takes 7 hours to build Mathlib, right? The growth the community wants to see is unacceptable, right? We have to address the scalability issues to make sure that Mathlib can grow at the rate the community wants, right? When we talk with many members of the community, they want to see, like, in 5 years, Mathlib would be 10 million lines. With the performance we have right now, it's infeasible, right? The turnaround now is almost 24 hours. If someone submits a PR to pull request to Mathlib, a contribution to Mathlib, will take at least 24 hours for the continuous integration, right? This automated process that runs in the cloud to check if your contribution is not introducing problems at Mathlib. It compiles. This is too long, right? If it keeps growing, right, it's going to be infeasible. So scalability is a big deal. There's a lot of engineering, but also designing new data structures, new algorithms, improving what we have. This is a big problem right now. Usability, it's another important topic, right? To make this system accessible, more attractive to a bigger audience. We made several improvements, and there are many commits. This joint work with Microsoft Research, KIT, CMU, people from all these different organizations contributing to make Lean more accessible. And it's a really sophisticated development environment at this point. You can, at any point, visualize the state of your proof. You can click and visualize the state of the proof. This info view on the right-hand side is not just text. It's a live object. You can click and zoom in these objects and get extra information. You can jump to the definition. You can get auto-completion. The traces, right? Automation is great, but it's really important. It's even more important to have good feedback when something doesn't work. One way we have is to create trace messages. The automation we build produce traces, and these traces are not just strings, but they are interactive objects. Right? Here, for example, this is a feature that Gabriel Ebner, I think I see him in the audience, implemented. This is awesome, right? You can zoom in, you can inspect the objects, and you can really understand what's went wrong, right? So having these interactive trace messages are super important. Another thing that is really cool is a project that's Wojciech. I don't know, I haven't seen him in the audience, but Wojciech implemented this. Oh, great. Yeah. This is great. I mean, you can declare your own visualizations, right? Here in the same file, you have mathematical objects like commutative diagrams, and you define it, your visualization, and the object, the same file, and you can visualize the objects on your info in the lean info view, right? We imagine a future where people will create their own visualizations. It will make it much easier to interact with the system, especially for people that are trying to understand the proof. They can visualize the proof. They can click anywhere and get a graphical visualization of the current state of the proof. The language, right? The Lean language is rich and extensible, has many different features. I think Andre yesterday gave a nice talk talking about, I think he says it's the vernacular, where you have coercions, overloaded annotations, type classes. There's a lot of machinery, right? This is on top of the foundations. The main point here that there is no spec. Nobody really knows how formal math should look like. We are learning it with the community, right? Our aspiration is that every new gadget should have a well-defined semantics, right? But this is something that we're always trying to polish, make it better, right? AI. It's impossible now to talk about proof assistance without talking about AI, right? I think one cool thing about formal mathematics is that it's a solid foundation for AI, right? Now we are seeing AI that can generate code. We are seeing AI that can generate proofs, right? But formal math makes sure that this AI can generate a proof or piece of code. It generates a proof that we can check if it's correct or not with the kernel. It can generate code equipped with theorems that state properties. Basically, it produces the code in a proof that the code has a property we want. Right? This is a future where you'll be able to interact with AI and make sure whatever the AI produces is indeed correct. OpenAI built GPTF, right? They use it to solve some problems from the IMO. I have one here. This problem is in a decidable fragment, but still, it's really cool. I mean, you can solve this problem using decision procedures, but still, it's really nice that their tool, if you use a decision procedure based on cylindrical algebraic decomposition, the proof is incomprehensible, right, to a human. Right? It's crazy. For most humans who will not follow the proof. It's a monster. But here he created the proof, and more important, it invented the terms that were necessary to prove this theorem. It was like the magical step is there. He invented the magical term, the B minus A, the C minus B, C minus A. It's like the AI here is doing the magical step. Another point to highlight here that is using tactics available in Mathlib, this nonlinear arithmetic tactic that's available in Mathlib. It's a combination here of large language models and the tactics that have been implemented by humans, by the Mathlib community. Another example is from Meta that was called Facebook in the past, right? They have this paper called Hypertree Proof Search, right? It's a combination of search and large language models. If you download the Linktree plugin for Visual Studio Code, it's integrated. It will suggest proofs for you, right? You have here the text suggestions. It's there. You make suggestions to you. And this is a really nice step in the right direction, right? We can foresee a future where these large language models are suggesting interesting tactics, are doing synthesizing boilerplate code for us. Many proofs follow the same structure, right? And it's not inconceivable to imagine large language models automating the process for us, right? Someone mentioned yesterday, oh, it's really hard to remember the theorems. I'm sorry, I forgot who says that. There were many talks. Remembering the right theorem can be taxing, and AI can help us with that. I think this is another great project built on top of Lean. Another one's Lean Chat, right? Zanjir and Ed built this tool. It's available already at VS Code Marketplace. It allows you to write statements in English, and you get back the Lean version of the statement, right? And it's an interactive process. You can interact like we do with ChatGPT, right? You can say that's almost correct. Just replace order with order half, and this interaction allows people that do not know the Lean syntax to state things in the Lean syntax, just communicating with the system in English, right? I think this was a nice demo of what will be possible in the future. Another example is Lean 8 by Ayush Siddhartha. I think he's online. Naveen is a colleague of mine from Microsoft Research India, and Anand, right? The tool is like Lean Chat, but more, I think it's more polished. You can write in comments in English what you want. Visual Studio Code, sorry, is a little bit blurry, but there is a light bulb here that you can click. And after you click the light bulb, it will convert what you wrote in English in a Lean statement, like Lean Chat. But there are many improvements. They have a paper describing the techniques. It's another promising direction, right? And Siddhartha also made a good point about Lean 4 when he presented this work. Also, like in Lean 3, the AI community wrote, they had to inspect the state of the system, and they had to hack the previous version of Lean to extract this information. Like information about the internal states of a proof, the internal states of the Lean system itself. In Lean 4, since everything is extensible, they do not need to build this infrastructure. They do not need to hack the system. Everything is available there. And Siddhartha made these good points that in Lean 4, everything that's needed to build these great AI assistants on top of Lean is already available in our API. Okay, we had many different applications using AI, using large language, what we call large language models. But what was in common with every single application I have shown in these previous slides is you could achieve the same by going to Lean Zulip and asking the question. Basically, they're automating something that humans know how to do really well. Of course, this is important, right? Zulip will not scale. If one day for mathematics, you have millions of users, it's infeasible to millions of people go to Zulip and ask questions, right? AI can automate the process. This is valuable. But there is another form of automation, right? That's not based on large language models. And here's I have an example of Marian. From Marian, I love this example. He presented at Microsoft many years ago, and is encoding math problems into sets, right? Today you have stat solvers, you have asymmetry solvers, you have a lot of decision procedures, testability checkers. They can do massive case analysis, right? You can do things that you can't solve this problem that's Marian solved in this paper by going to Zulip. There is a massive amount of case analysis being done here. This is a different kind of automation. It's a different way computers can help mathematicians. And I think this is important to keep in mind. large language models can help us a lot, automating what humans can do, transferring these kinds of feedback the community gives you at Zulip, right? Scaling that. And here you have this kind of massive case analysis, problems that would be impossible for humans to attack by themselves, right? And I think it's important to keep in mind. Engineering, right? Yes, there's a lot of engineering. People ask me all this time at Microsoft Research, right? They say, wow, it feels like this project has a lot of engineering. Yes, there's a lot of engineering. And it's challenging because you need a lot of engineering. The cost of the projects increases too, right? You have to, just to build the project, right? You need special support. Yesterday, we had this picture of the Tower of Babel, right? And one thing for me is like, what's going to happen in the real Tower of Babel? God stopped the construction, right? For us, what is going to happen is my main fear is we run out of money. The tower stopped being built because we don't have money to keep it going up. Just to put in perspective, people hope to get Mathlib to 10 million lines in 5 years. Some people say in 10 years, if the community keeps growing at the rate it's growing, it's not infeasible that we will be 100 million in 10 years. Suppose that this dream happens, right? Suppose it's 100 million lines of code, right? This tower now is bigger than the Facebook code base. It's bigger than Linux, right? It's bigger than Windows, right? All these projects, just infrastructure to keep the tower going up, it's insane. For example, at Facebook, they have 8 engineers, highly paid engineers, just to keep the build, just to take care of the build system, just to make sure they can compile the Facebook code base. If you have 100 million, it's bigger than the Facebook code base, right? All the infrastructure you need for 1 million, the growth is not linear. The cost does not grow linear today, right? And Facebook is really frugal, right? I remember one of my former managers, he went to Meta, and he was in a group building the build system for Microsoft. His group had 70 people, right? And he arrived at Facebook, said, wow, it's just 8 guys doing that? But 8 guys are super expensive, right? I mean, this for a research project like Mathlib, this is super expensive. To keep the project alive is what keeps me up at night. One way is to have impact on software verification, hardware verification. You want a system like Lean to have stakeholders in many different organizations. It's the only way I see to keep the project alive in the long term. But I think this is one of the most important challenges for projects like that. And I think everybody in the Lean community don't want to see the tower stops the construction because we ran out of money. Okay, this part was sad, but I want to talk a little bit about cool things. Community excitement is a big deal. I mean, people use Lean for things that we didn't expect. Here you have an example from Thomas. Because Lean is extensible, he created an extension that you can create animations, like this one here. Basically, he's communicating between Lean and Houdini, is a system he works on. And he's saying, like, wow, this is really cool. I can annotate a function, arguments, and automatically generate functions, derivatives, proofs of smoothness. And he's saying, look, here's the Hamiltonian definition for the above system. And this small piece of code, right? This argument X is smooth. Just all his extensions, this is not part of Lean, right? All these 2 lines on the bottom, this is extensions he created by himself without ever talking with us. Well, he asked questions on Zulip, but that was it, right? And we're super excited to see this kind of application. We think we'll find many other applications like that in the future. And we think this is really exciting. Another cool idea we have seen on Zulip is this idea of auto-refactoring originalization. Ricardo Brasca, I saw this message from him. He was saying, Mathlib has many classes like fields, strings, they're all represented as classes in Lean. And sometimes you state a theorem and you are using something, you state the theorem saying that you use a field, but you could have used as a ring. And you can write a simple tool that tries to generalize your theorems automatically, that tries to move up in this hierarchy or try to remove assumptions and try to check if you can still prove the theorem. You can do that because you have the kernel, right? We have the kernel that will check if your proof is still correct. And you can automate the process. And he's saying, wow, imagine that if you can do that automatically, right, with the linter, with this kind of tool. Now, this is the first thing, this is cool, but it's even cooler that you can propagate the generalization. Suppose that you generalize the results in a 50 years old paper, right? How do you propagate, right? It's a really hard task to propagate these results, right? But with formal mathematics, this propagation is for free, right? So you can automate. It's the idea that you can treat math as data, right? You can change it. You can write programs that will change it. You try to improve it. The same way we do software, right? The same way you have software that can compile programs, that can transform programs, that can make them better, that can write linters to tell users about defects in the software automatically. You can have the same thing for mathematics. And this is really cool, right? It's a new possibility. Thank you very much for your attention. The main message I want is that to communicate today is that Lean is extensible to Improver. If you want to learn more about Lean, go to the leanprover.github.io. It's easy to install. We support decentralized collaboration, right? I think it's an important idea that you can extend Lean using Lean itself and you have formal proofs, formal objects. I believe the Mathlib community will change how mathematics is done and taught, right? And the final message, I see many people in the Mathlib community telling this message, but I think it's really important. It's not just about proving, making sure your results are correct, but for mathematics, it's way more than that. It's about understanding complex objects, understanding proofs, getting new insights, navigating through these objects, right? Helping you to achieve more. Empowering, you can now have AI, you can have assistants, you can have these linkers, you can collaborate with people you don't know. I think the possibilities are endless. Thank you very much.